We generally believe that when we add automated safety systems to our machines, to our vehicles, our hospitals, we're making these complex operations infinitely safer. We naturally assume we're finally eliminating that fragile, unpredictable element of human error.
But what if there's a structural reality where these exact systems actually guarantee eventual failure? Take commercial aviation, for example. Overall safety is absolutely higher than it was in the past. Yet when modern crashes do occur, a pretty terrifying, persistent pattern shows up. We find highly trained pilots staring at their digital screens, completely perplexed, literally asking out loud, "What's it doing now?" as the plane descends. The very systems designed to save them have become completely opaque.
Picture a heavy iron weight suspended high in the air by a simple hand-cranked steel winch. A human is physically gripping the crank, feeling the tension pulling against them, keeping that weight from falling. It requires constant, active effort. The tension is felt right there in the muscles. The risk is immediate, and it's incredibly tangible.
Section 1. Operators becoming observers.
So when holding that crank is deemed just too risky or too tiring, the logical next step is to let a complex, automated system take over the physical and cognitive workload. We transition from being active, hands-on operators to passive system managers. Airplane pilots rely heavily on digital flight guidance systems now. Doctors use AI-assisted diagnostic tools. Accountants rely on intelligent decision aids. Structurally, the human is relegated to a passive observational role. You aren't really flying the plane anymore, are you? You're managing the computer system that flies the plane. That direct connection to the task is severed.
An automated ratcheting gear is installed on the winch. The human no longer has to hold the crank. The automated mechanism locks that tension firmly in place, so the human physically takes a step back from the machine, completely trusting the gear to hold the heavy weight. The effort is completely removed, and the tension is no longer felt.
Section 2. The loss of capability.
Now, when we step back and become these passive observers, there's a direct, measurable consequence. A slow, silent degradation of human capacity begins to take hold right behind the safety of the new system. Consider a 2025 medical study in Poland. Researchers looked at doctors using an AI-assisted system to detect polyps during routine colonoscopies. Before routine exposure to this AI, their detection rate was 28.4%. But after getting used to the AI, it unexpectedly dropped to 22.4%. They became measurably worse at their core task simply by being exposed to the automated help. Their baseline skill literally eroded.
Now, this isn't human laziness. It's something called de-skilling. It's the process where skilled labor is eliminated by the introduction of automated technology. Because the system is now handling the complex decisions, the operator is stripped of the daily, rigorous practice required to actually understand their environment. They lose that tacit, intuitive knowledge required to jump in and intervene manually when the automation inevitably fails.
This is the exact moment the human entirely releases the crank. They aren't just physically disengaged, they are cognitively disengaged. They've totally lost the muscle memory of the tension. Think about it. If that automated ratchet were to suddenly slip, the human no longer has the grip strength, the focus, or the reflex to catch it. That physical connection to the danger has completely dissolved.
Section 3. The complexity of safety. Engineers, of course, recognize this human fragility. They know human operators become distracted and de-skilled over time. So the logical engineering response is to add even more layers of automated safety to protect the system from the increasingly unreliable human. To make absolutely sure the iron weight doesn't fall, a massive safety enclosure is built around the entire winch, and it's locked shut. The physical system is now completely inaccessible. The very constraints designed to protect the system have permanently isolated it from human reach. There's no longer a way to physically intervene, even if someone desperately wanted to. When you layer safety system upon safety system like this, you create a tightly coupled architecture. The Apollo 13 Review Board actually noted that the disaster resulted from a combination of mistakes coupled with a deficient and unforgiving design. The system was so deeply interconnected in order to be safe that it became entirely unforgiving of any unexpected anomalies. A failure in one highly optimized node instantly transmits to the rest of the structure. The result of all this is a pretend reality. Take the tragic ValueJet Flight 592 disaster, which was caused by improperly loaded hazardous cargo. The maintenance manuals for that aircraft documented all the necessary procedures. They were technically perfect, but they were so incredibly vast, so completely unreadable, that operators couldn't possibly follow them in the fast-paced real world. The sheer volume of safety procedures created an unworkable maze. The system was only safe on paper.
Section 4. The normal accident.
So, what's the inevitable result when an unexpected anomaly strikes an environment that is perfectly safe, tightly coupled, and managed by a completely de-skilled operator? Well, aviation engineer Earl Weiner points out a rather fatal paradox. He says automation reduces the operator's workload when things are light and easy, but it spikes the workload to nearly infinite levels precisely when things get heavy. Exactly at the moment the system acts in an unexpected way, the isolated, de-skilled human is suddenly asked to decipher a massive cascade of incomprehensible digital warnings. The human is overwhelmed exactly when they are needed the most.
This is what's known as a system accident, an unanticipated interaction of multiple failures in a complex system. It's not just a broken part or a single, simple human error. It is a catastrophe that emerges precisely because perfectly safe, complex components interact with each other in ways the original designers never even foresaw. The complexity itself becomes the failure mechanism.
The safety systems themselves add fatal complexity. In disasters like the 3 Mile Island nuclear meltdown, investigations showed it really wasn't just management or operator ineptitude at fault. The interactive complexity of the safety valves and the warning lights caused a cascade of failures. The overlapping safety layers meant to save the plant were the exact mechanisms that guaranteed its failure. The safety structure obscured the true state of the core until it was just too late.
Section 5. Structural irreversibility.
Once a system reaches this critical level of complexity, we hit a really chilling threshold. Deep behind that safety enclosure, completely unmonitored by the human, the ratcheting gear experiences an unanticipated stress. The gears bind unexpectedly. The physical system has reached its inevitable breaking point, and the unmonitored mechanisms are failing in absolute silence.
The human suddenly realizes what's happening. But remember, they haven't held that crank in years. They lack the physical and cognitive grip strength to stop it. And honestly, even if they somehow possess the strength, the safety enclosure is permanently locked. It prevents manual access entirely. They can only stand there and watch the weight fall. The isolation is complete.
The system can no longer be safely reversed, and it can no longer be manually saved. This complexity becomes permanently locked in. As Boeing engineers have noted in the past, once automated capacities are added to flight management systems, they become impossibly expensive to remove due to massive certification requirements. Even if they go completely unused, they just lurk unseen in the depths of the architecture, waiting to interact in unforeseen ways. The system is structurally paralyzed by its own safety.
Perfect optimization guarantees structural failure. When a complex system fails catastrophically, whether we're talking about an airplane, a nuclear power plant, or even a global financial market, it wasn't actually breaking down. The system was simply following its tightly coupled structure. It was the normal, completely irreversible output of a machine that was designed to be perfectly safe.